There are typos on quizzes 5 and 6. The max should read as min. So I have already corrected them so you see here, I have already corrected the max to min in quiz 6, and the same thing with quiz 5. It should read as min, not max. So if you have already printed quiz 5 or quiz 6, please make the corrections, okay? I apologize for the typo. All right, the typo is that it read as max, which is not correct. It should read as min, not max, okay? All right, guys. Now, before I talk about the lectures today, there's a second announcement I'd like to make. It's about the lab sessions for this week. You know, we have lab sessions, 5 lab sessions this week, and I would like each session attended well, because the week before last week, we did not have a good number of students attending the lab sessions, all right? So please do attend the lab sessions. There are 2 tomorrow, there are 2 on Thursday, and there's 1 on Friday. So please go to those sessions, right? Now, what I like to say is just a brief introduction to the lab sessions this week, right? All right, if it is a right? If you have a random variable x, right? Let's assume for the moment it's a continuous random variable. Then its PDF is denoted by little f of x, and its CDF is denoted by capital F of x, and is defined to be this, right? And its quantile functions right? Its quantile function is defined by this equation here. The probability that the variable x less than or equal to q of p is equal to p, right? And finally, this is comma, okay? right? There are 4 things you need to know. Come on, guys. Can you be a little bit early if you're coming, guys? There are 4 things you need to know for any random variable. Number 1, if it is a continuous variable, is the PDF, right? Number 2 is the CDF, which is defined by this. Number 3 is the quantile function, which is defined by this. And number 4 is a random sample, which can be generated by this equation here, that xi equal to q in brackets ui, where ui are uniform, IID uniform random variables, right? Now, what I'm going to tell you is how to do this in R. This is what you're going to learn this week. How to do this in R. So, for example, continued intro to right. Now, if you take the normal variable, let all right, suppose x is a normal variable with mean equal to 1 and variance equal to 1. In this case, the following command. Can you guys keep quiet, please? This command in R will compute so it will compute the PDF of n11 at the values specified by x, right? And the following command, pnorm, right? The pnorm command will compute the CDF of n11 at the values specified by x. And the next one, qnorm, right? This command qnorm will compute so it will compute the quantile function q of p, which is defined by this, right? It will compute q of p of the normal variable 1, 1 at the values specified by p, right? That's what qnorm does. And finally, rnorm, if you type something like this in R, what it will do is it will right? But it will generate a random sample, x1 to xn, where each element has the normal distribution 1, 1, right? So IID means independently and identically distributed, right? So these are 4 commands, that apply for, in this case I have illustrated with the normal distribution, but it can be applied to any other continuous or discrete distribution, right? So it's the D and the P and the Q and the R. So D for density, P for CDF, Q for quantile function, and R for random sample, all right? So these 4 letters can be applied to any distribution, not just the normal distribution. And the purpose of the lab session this week is to learn how you can use these 4 things for any distribution, right? All right, guys, any questions on this? By the way, if you came late, let me just to summarize what I've done so far. If you came late, there are typos in quiz 5 and quiz 6, right? That's if you came late. The typo is that the max, if you have already printed out quiz 5 or quiz 6, please change the max to min, right? You follow what I'm saying? This is not rocket science, right? We just changed the max in the quiz 5 or quiz 6 to min. And I have already done that online. So if you go to my website, you will see it's already changed to min, right? And the same thing with quiz 6. It's already changed to min. All right. Now I'm gonna revise now what I did last week, and also do some examples to help you to do quiz 5 and quiz 6. Right now, last week we talked about point estimation. The point estimation is an important part of statistics. So I started with an example with the population, parameter, sample, and estimator, right? So in this case, you can have a number of estimators for theta. Hello, guys. Are you listening? You can have a number of estimators for theta, where theta in this case represents the average height of men in the UK. So the question is, which is the best estimator? How do you decide which one is good and which one is not, right? And to do that, I introduced 2 criteria. The first one is known as the bias. The second one is known as the MSE, or the mean squared error. These are the definitions. The smaller the bias, the better the estimator. And the same thing with the MSE. The smaller the MSE, the better the estimator, right? Now, suppose you have 2 estimators, theta 1 hat and theta 2 hat. So this is how you would select the better estimator. So if the absolute value of the bias of theta 1 hat is smaller, then you would choose theta 1 hat. And similarly for MSC, right? Then I introduce 3 definitions. Unbiasedness. Unbiasedness means that the bias is 0, which is a good thing, right? Asymptotically unbiased means that the limit of the bias is 0, which is again a good thing, but not as good as the unbiasedness. And the third thing is consistency. Consistency means that the limit of the MSC is 0 as n approaches infinity, which is again a good thing, right? Then I listed 3 properties. The first property, which I have already proved. The second, I have already proved. The third one, I will prove today, right? Are you guys listening? The third one, I will prove today. So this is the proof of the first property I gave last week on Thursday. Did you guys follow this proof or not? Are you okay with this proof, guys? I'm not going to ask you this in the exam, but it is good to know this proof. If you can't follow this, see me in person or Zoom me 24/7, right? And this is the proof of property 2. Are you okay with this, guys? Yeah? Okay. Seems some of you are still sleeping. Huh? Come on, guys. Why don't you guys I mean, any questions you guys have, just Zoom me, okay? 24/7. I'm online all the time. Okay, now let me prove property 3. This is property 3, so I'm going to prove it now. So this is proof so property 3 says that if the it should say there's a typo here. Is k is a constant, k is a constant. K is a constant. It should say k times theta, not k, right? So to prove that this is unbiased for theta, we need to prove that the bias of this is 0, right? So the bias, as I told you last week, is defined as this, right? And this is, because k is a constant, you can take it outside. Right, so this becomes 1 over k times, and using this, k times theta minus theta, which is theta minus theta, which is 0. Hence, all right, so the proof is fairly straightforward, okay? But the property 3 should have said the expectation of theta hat equal to k times theta, where k is a constant, right? So we have now proved that the bias is 0, hence the estimator must be unbiased, right? Are you okay, guys? Yes? No? You're right, man. Okay? Okay, good. Now I'm gonna do lots of examples, starting with example 1. I know some of you like me to do more examples, so let me start with example 1. So these examples will help you to do quiz 5 and quiz 6, okay? So right. And you read this example 1. So you have a random sample from a normal distribution with parameters mu and sigma squared, and we have an estimator for mu, which is the sample mean, and we want to find the bias and the MSE of mu hat. Okay? All right. Can you guys keep quiet, please? So the first thing you want to find is the bias. So remember, the bias is defined as this, right, which is this. Now I'm going to take the expectation inside. So Now, we done the normal distribution. What's the expectation of xi for normal? It's not 0, so it's mu. We are assuming it's mu. See, we are assuming IID mu. So it will be all right. So this is 1 over n times mu, which is 0, right? So this implies that mu hat do you follow what I've done, guys? Guys, you okay? So I have shown that the bias of the estimator is 0 by following the definition of bias. Okay? The next thing I want to find is the MSC, right? I want to find the MSC of mu hat. Now, the MSC of mu hat is, because, remember the property 1, property 1 says that MSC is the same as the variance of mu hat plus the bias squared, right? Now we have shown that the bias is 0. So this guy here is equal to 0, right? So what we have is the variance of 1 over n times the sum of xi. Okay? Now if you take the variance inside the brackets, you will see this. Okay? Remember, when you pull a constant outside the variance, you need to square it. So when you pull the n outside, it becomes the square of n, right? Now the variance of xi is what? Xi is normal with parameters mu and sigma squared. So the variance is sigma squared. So this becomes sigma squared divided by n. Right? And this, as n approaches, infinity, this approaches 0. Hence, mu hat is consistent for mu, right? Remember the definition of consistency is that the limit of the MSC as n approaches infinity must be 0, which is the case here, right? All right, so that's example 1. The next example is going to be crucial for you guys. All right, so this example will help you to do quiz 5 and quiz 6. Right, so you have a random sample from a distribution that has this as a CDF, right? And theta hat is defined as the minimum of the data, right? And we want to find the bias in the MSC. Okay, for examples like this, what you need to do is first, because we don't know the distribution of the minimum, right? So the first thing you must do is to find the distribution of this, right? So before you can find the bias or the MSC, you need to work out the distribution of this. So right? And this you can write as right? You can write like this. Now, think carefully. Now, if the minimum is greater than z, if you have a sequence of numbers and their minimum is greater than something, what can you say about each? I mean, this will get you. Yeah. If this is the same as saying that x1 is greater than z up to xn is greater than z. Do you follow me? Why? Because the smallest value of a sequence of numbers is greater than z means that each value must be greater than z, okay? And because of independence, because x1 to xn are independent variables, you can write this as like this, right? And because x1 to xn are identical variables also, because of the assumption of identical, right, you can write this as the probability that x is greater than z to the power n. Yeah, that's using the fact that x1 to xn are identically distributed, right? And finally, you can write this guy as 1 minus the probability that x I know it looks long, but once you start doing this, it will not be. Now, we are given the CDF of x as this, right? So this will be 1 minus 1 plus like this, okay? Are you with me? And this simplifies to 1 minus e n theta minus n z. All right, so this is the CDF of, so let me put it here. You can see it better maybe. All right, so to summarize what I've done so far, I have shown that the CDF of z is equal to 1 minus e n theta minus n z. Okay? So this implies that the PDF of z is simply the derivative of this, which is, I'm sure you guys know how to differentiate. So if you differentiate this, you get you get this, right? Okay, so this is the PDF of that. All right, now we can come to finding the bias and the MSC. So let's start with bias first. So the bias of theta hat, which is the same as the bias of Z, right, is equal to the expectation of Z minus theta, okay? Now, to find the expectation, we need to use the PDF, right? Now, this is where this should be x greater than theta, guys. Sorry. Okay. Now, would you know how to integrate this, guys? This will be, it's not difficult to integrate. Do you know, guys, integration by parts is something you probably did in your nursery? Integration by parts, yeah? If you did integration by parts, do you guys remember or no? Okay. This is what I'm doing now, by parts. Integration by parts. Don't tell me you don't know. Don't tell me you don't know integration by parts. So this is what you get, right? And the limit at infinity is 0. The limit at 0 is 0. And the integration of this is not difficult. Like this, okay? So, correct me if I made any mistakes. Let me know, please. So this would be n at infinity is 0, so it's going to be 1 over n times 0 plus right, minus theta. Okay, so this is going to be oh, sorry. Did I do this right, guys? I mean, sorry, I think I made a mess up. Did I do this right? I don't think. You've been checking my calculus, sorry. I think the limit at infinity is 0, right? And the limit at theta is not 0. So it's going to be sorry, man. No, let me start again. Let me start again from this. Excuse me, sorry. Right, let me, after this step, right, I think I made a mess up here. I'm too old to know all this. Right, integration by parts, I think, is correct. So this would be n en theta. The limit at infinity is 0, and the limit at theta will be plus divided by n, right? And then you have 1 over n. The integration of this is e of minus n like this, okay? I'm sorry about this, guys. Minus theta outside, okay? So then you have n e n theta divided by n, and plus the limit at infinity is 0, and minus theta, right? And then if you simplify this, minus theta. So this would be theta plus 1 over n minus theta. Correct me if I'm making any mess up like before. So n and n cancels, you get, so this is 1 over n. All right, so the bias, what we have shown so far is that the bias of theta hat is equal to 1 over n, right? So hence this implies that theta hat is a biased estimator. Is a biased estimator of theta. However, since the limit of the bias as n goes to infinity is 0, remember the limit of 1 over n is 0, right? Theta hat is asymptotically unbiased for theta, okay? It's asymptotically unbiased for theta, since the limit is 0, right? So do you follow what I've done? I apologize for this error, but it's just simple integration by parts, guys. If you do integration by parts, you get this. Then you simplify through this. You get the bias to be 1 over n. So hence the estimator is not unbiased, or in other words, the estimator is biased. However, it is asymptotically unbiased since the limit of the bias is 0, right? Okay, guys, so that's only one part. Now, to do the second part, so far we only done the bias. To do the second part, which is the MSC, you need to use this formula, right? So this is going to be the variance of z plus 1 over n squared, right? Guys, listen, please. The variance of z you can write as the expectation of z squared minus the expectation of z power 2 plus 1 over n squared, right? Now this would be finding these two, you will need to use integration by parts one more time. So that's more work for you guys. So for this, you need to use this, right? And for this one, you can. We have already found out what the expectation of z is, right? That is this plus 1 over n squared. So all you have to do is just apply integration by parts to work out this integral, guys, right? Which is not too difficult, but come on, guys. Right, this. Now, without going into too much trouble, can somebody tell me what this is? I don't want to get into the same problem we had earlier, which, all right. Okay. So by parts, if you do parts, right, for this integral here, you get n, e, and theta, z squared, e, right, and then you have a plus 2 divided by n, integral from theta to infinity, this is theta, okay, theta to infinity of z dz, and then minus something like this, okay. Now you should take the limits. At infinity is 0. At theta it will be theta squared e of minus n theta divided by n. And this integral here, we already know what this guy here is from the first part, right? So if you look at the first part, guys, it is something like, I'm trying to figure, all right, it's this guy here. So it's going to be 2 divided by n theta I know it looks like a lot of calculus, but I mean, you guys did a whole semester of calculus, so you should know what this is. All right, this is what you get, right? So this is your MSc. Now you should simplify this, guys. If you simplify this, you will get what you want. So this will be, this goes, so it will be theta squared, and the n and the n cancels. There will be a 2 times theta divided by n plus 1 over n squared. Correct me if I'm wrong. It's quite possible I may be making some mistakes here. These two cancel, so it's 2 times then minus theta plus 1 over n squared plus 1 over n squared, right? Okay, you with me? Oh, you lost already. Come on, guys, wake up. Okay, so this will be theta squared will cancel, 2 theta n will cancel, so you get the final answer will be 1 over n squared, which is very neat. You see, after all this calculus, we get this as the final answer. Is it not? I mean, is it not beautiful? Is it not? So this is your MSC. So what we have shown is that the MSC of theta hat is equal to 1 over n squared. Right? Now, to check consistency, we need to find the limit of the MSC, right? So the limit of the MSC as n approaches infinity is the limit of this, which is 0. So hence, theta hat is a consistent estimator of theta. I mean, the reason I have done this example, although it took me ages to do it, is to help you to do quiz 5 and quiz 6, right? All right, now you should be able to do quiz 5 and quiz 6 based on what I did. But I only did 2 examples, but when I see you guys on Thursday, right, I will do at least 3 more examples, right? I know, okay, I will do at least 3 or 4 more examples on bias and MSC, right? You guys okay? Or you lost? Do you see what I've done? It's just basic calculus, guys. You did 1 full semester of calculus, so you should know what I was doing. So I see you guys tomorrow in the computer classes or computer sessions. Have a good day, guys. Okay, thank you. All right. Hello, how are you, sir? Have a good day, man. Yeah, see you. Hello. Yes, you have a question.
In this step, you calculate PDF of the this, right?
The PDF, yeah, the PDF is here, man. Look, what you've written is wrong. This is the PDF.
Yeah.
Hey, Darren, how are you? You're still working? It's not good for your health. You should take some rest. Yeah. Huh? Okay. How are you? You have a question? Are you okay? This is the PDF.
Yeah, I mean, you got it from...
If you differentiate this with respect to Z, this is what you get.
So here theta is a constant.
Yeah, that's a constant, sir. Okay. Have a good day, man. Yes.
Why the EX is this one?
That's because we already did it here, ma'am.
Yeah,
We already found that theta plus 1 over n through this. You see, E of Z is this. E of Z minus theta is this. Yeah. Hey, you. How are you? You have a question?
we have midterm test.
No midterm, no. There's no midterm. You sent me an email yesterday, right? No, there's no midterm. Did you check my emails? Check my emails. There's no midterm. It's only weekly quiz and the R coursework, which is due on the 21st.
Okay.
Yeah, there's no midterm test. Hello, are you Matthew?
2 over n squared. 2 over n squared rather than 1 over n squared.
Is it 2? How did I get 2? How did I miss it out?
The theta squared cancels, you get 2 over n squared squared here, and then minus 1 over n squared, and then plus it
Plus,
again.
oh yeah, you are right. I'm being so stupid today. Yeah, thank you, man, thank you.
And I take over the 2 minutes.
Yeah, that's 2 n squared. Yeah, you're right. But the answer is the same. Yeah. Yeah. Thank you. Thank you for pointing that out. I made a lot of errors.
What I can use is, it should be
2 n squared. Yeah. Yeah, that's what I changed now. It's 2 n squared. Yeah, it's 2. Yeah, it's 2 n squared now.
can I take over?
Yeah, yeah, sure. Hello, good morning. Sorry, today I had a terrible day.